Instantaneous rate of change. So in order to find the instantaneous rate of change, what happens is you are calculating the average rate of change over an interval, but you're looking for that interval to approach zero. So the instantaneous rate of change is the limit as the length of the interval, which we'll call h, and you'll see that in just a minute, approaches zero. So if we look at our definition here, we're looking at the change in x. Change in x is approaching zero. So that distance between our initial x value and our final x value is approaching zero. So the instantaneous rate of change is the change in y over the change in x, which looks like the limit as x2 approaches x1, because if x2 is approaching x1, then the distance between our two x values is approaching zero. And it will look like our f of x2 minus f of x1 over x2 minus x1, which should sound very familiar because f of x2 is really y2 and f of x1 is really y1. So this should look exactly like our y2 minus y1 over x2 minus x1 slope formula that we've been using before. The only difference here is now we are trying to make our two x values, x2 and x1, get extremely close together, so much so that they become the same point to have that instant. So let me show you what this looks like. For our first question, we have g of t. Now in our formula, we have f of x. Here we have g of t. It's the same idea, just with a different named formula. So what we're looking at here is the limit as the change in x. Well, the change in x this time is going to be the change in t because our variable is t. So our delta t is approaching zero. And our limit is, well, it would be f of x2, but because we have g and t, it'll be g of t2 minus g of t1 all over, it would be x2 and x1, but because our variable is t, not x, we'd have t2 minus t1. Let's think about this for a minute. If our change in t is approaching zero, that means that we could say T2 is approaching T1. And if T2 is approaching T1, well, then that means that we have two values. One is T and one is 1, because that's what's given to us in the original. So another way we could write this is the limit as T approaches 1. So our t and our 1 are getting closer and closer and closer together as our t2 and our t1 values are getting closer together. And then that would look like f of, well, t2 is just t. So that would look like f of t minus f. Well, in this case, it's g. So let me put the g's in so it matches. Minus g of t1 time 1, in this case, is 1. All over, and then we have our second t value is t, and our initial t value is 1, so t minus 1. Let's evaluate this. So this becomes the limit as t approaches 1. Looking at our function over here, g of t means our function evaluated at t, which in this case it already is. So it looks like t squared plus 4t minus g of 1 means our function evaluated at 1. I'm going to put it in parentheses so I don't lose any of my signs. So this means take out the t and put in the 1 all over t minus 1. So this equals the limit as t approaches 1. Now let's clean this up. 1 squared is 1 plus 4 is 5. So that means in the numerator here, we're going to have t squared plus 4t minus 5 all over t minus 1. Well, t squared plus 4t minus 5, that'll factor. So we have the limit as t approaches 1. Our denominator is not going to change, so let's keep our t minus 1 right there. Now in the numerator, we need to factor this. So we need two numbers that multiply to -5 and add to a +4. So that looks like we'll have t plus 4 and t minus, let's try that again, t plus 5 and t minus 1, because t times t is t squared, t times -1 is -1t. 5 times t is 5t. 5 times -1 is -5. So our -t plus 5t will give us positive 4t. Now this and this will cancel. So now we're left with the limit as t approaches 1 of t plus 5. Now we have no more restrictions on our limit. We're not going to be putting in our value and getting 0 in the denominator anymore. So we can go ahead and evaluate our limit. We can put our 1 in for t. And when we do that, we don't write the limit anymore because we are evaluating, we're putting the 1 in. So 1 plus 5, that gives us 6. So that means our instantaneous rate of change for g of t equals t squared plus 4t when t equals 1 is going to be 6. Let's look at the next one. Speed is a rate of change. Think about an object traveling. Think about a car driving, a plane flying. If it's flying at a speed, that means it's going. It's changing its location. So speed is a rate of change. So when we're looking at a rate of change, we are looking at something moving and traveling. So look at number 2. Suppose an object travels a distance of f of t miles after t hours. Write an expression for the average speed of the object in the time interval from t equals 3 to t equals 3 plus h. So if we think about our equation we just had, this would be our x2. This would be our second time interval. This would be our x1. This would be our first time interval. If we are looking at our equation from above, remember our equation said f of x2 minus f of x1 all over x2 minus, x1. And we put in what we have now for our x's right here. This would look like f of 3 plus h minus f of 3 all over 3 plus h minus 3. And that is going to simplify to f of 3 plus h minus f of 3 all over h. Now remember, our idea here is that x2 and x1 are getting closer and closer and closer and closer together. So that means if you look at the next part, when we're thinking about our instantaneous speed at our time interval of 3, that means that we're thinking about this h right here going to 0. Because remember, h was our change in time, our x2 minus our x1, our second time value minus our first time value. So that means that we're looking at an instantaneous rate of speed of the limit as h approaches 0 of f of 3 plus h minus f of 3 all over h. Now this is going to become important because if you look a little bit further down, this right here becomes the definition of our derivative and our tangent line. So when we're looking at a tangent line is a geometric interpretation of an instantaneous rate of change. A tangent line, remember we had a secant line here in the blue, and as we got those 2 points of the secant line closer and closer and closer together, it became a tangent line. So the tangent line right here is where our slope is approximating, and it is our instantaneous rate of change. So remember, the secant line was the average rate of change over x2 and x1. So what we're saying now is we're taking that x2 and x1 and getting them closer and closer and closer and closer and closer and closer and closer together. As they get closer together, that becomes the instantaneous rate of change, and that represents our limit. And that also becomes the definition of our derivative.